great pleasure to have Marc Lackenby, who will talk about polynomial upper bounds on Reidemeister readers.
Great. Thank you very much for the invitation. Pleasure to be in New York as ever. So today I'm going to talk about some very elementary questions in knot theory. Okay. I know what the problem is. Hold on a second. Yes, right, here we go. Right. Initially I'm going to talk about the unknot. And I'm going to ask, given a knot diagram, can we decide whether it represents the unknot? Okay, so as I'm sure you all know, the answer to that question is known to be yes. It was solved by Harkin about 50 years ago, and since then there have been many other positive ways of answering this question. But I'm going to be interested in the most elementary approach possible, involving Reidemeister moves. So, first thing you notice when you're studying this problem is that there's probably no easy answer to it. So, for example, there's this diagram of the unknot due to Loritz, which was discovered in the 1930s. And it has the property that it is an unknot, and hence there's a sequence of Reidemeister moves which takes it to the round diagram with no crossings. But it has the property that for any such sequence of moves, you have to increase the crossing. So you have to make it more complicated first before you can simplify it. So the most naive conjecture that one might make is that there's always some Reidemeister move which reduces the crossing number is false. So you may well say, well, Reidemeister moves are probably not the right way of tackling this problem. What about other more sophisticated or complicated moves that one could make to a knot diagram, which would be guaranteed to simplify it in the case of the unknot? But then the thing is, you can get some pretty nasty diagrams of the unknot. This, for example, is a diagram essentially due to Harkin, and it's designed to be a counterexample to just about any conjecture that one may make about how to simplify the unknot. So the conclusion that you draw from this is that there's probably no simple way of being able to detect the unknot. Okay, so as we all know, any two diagrams of a knot differ by a sequence of Reidemeister moves, and there they are. And for our purposes, what this has many uses, but for our purposes of recognizing the unknot, this has the consequence that if you happen to have a diagram of the unknot, you'll always eventually be able to prove that it's the unknot. Okay, the reason is, you take your diagram, you apply all possible Reidemeister moves to it, find many, and you get a collection of diagrams. And then for each of those, you apply all possible Reidemeister moves, and so on. And you get an increasing collection of diagrams of your knot. And you know, because of Reidemeister's theorem, that if it's the unknot, you'll eventually come up with a sequence which takes it to the round diagram.
How about trying to compute the hyperbolic volume of the complement center?
How do you do that?
Who knows?
Well, I mean, it's a good question. So, how might we solve the problem by trying to find a hyperbolic structure? Well, how long does it take to find a hyperbolic structure? It turns out that there is an algorithm due to Casson and Manning, which, if a manifold is hyperbolic, will compute a hyperbolic structure on there. But we don't know how long it takes. And, yeah.
If you're willing to settle for braids, you can do it without increasing coursing number at all.
You mean without increasing the braid index?
Braid index or coursing number.
What moves are you going to use?
What?
What moves are you going to use?
The moves are exchange moves and just braid words.
Right. Yeah, so...
And then there's a sequence that decreases, that's non-increasing on grade index.
right, so you have to allow yourself to conjugate, yeah?
Yeah.
In which case, do you stay... Well, what I'm going to
just
describe
saying that.
is
I'm just mentioning the existence of
yeah.
such a sequence.
Yeah, so what I'm going to talk about is very similar to that. I mean, the issue in the case of exchange moves on grades is you don't have a finite list of possibilities. So you don't necessarily get an algorithm, whereas with Reidemeister moves you do only have a finite list of possibilities.
Okay.
Okay, but we'll see how there is a solution which blends the two, which isn't due to me, it's due to GTiNY2013. So if you knew in advance how many Reidemeister moves you needed, you would have an algorithm to detect them. Because what you could do is you could just apply all possible sequences of Reidemeister moves at most that length, and if you knew in advance that you would get it down to the trivial diagram at that time, if it was the unknot, and if you hadn't therefore got it down to the trivial diagram at that time, you could say, I give up, this is definitely not it. Okay, so just in terms of Reidemeister moves, an a priori upper bound on the number of moves that you need gives you a procedure for detecting the unknot. Now, I've got to be a little bit careful here. It's not just a priori, it needs to be computable. And in fact, actually, you have the following easy theorem, that the following equivalent, that there is an algorithm to decide whether a knot diagram represents the unknot. And there's a computable function, f, from the natural numbers to the natural numbers, such that given any unknot diagram with n crossings, there's a sequence of at most fn Reidemeister moves taking it to the trivial diagram. Okay? So these are equivalent, and I've shown you one direction of that equivalence. I've shown you that if there's a computable function, then there's an algorithm to detect the unknot. Conversely, let's just quickly see why the converse holds. So suppose we have an unknot detection algorithm. Why does that give you a computable upper bound of Reidemeister moves? So what you need to do is, given an n, natural number n, you need to have a computer compute f of n for you. So what it does is it enumerates all diagrams, all knot diagrams with n crossings, easily done, and it sorts them out into two camps, unknots and the rest. It does that using a hypothesized detection algorithm. Then, for just the unknots, what it does is, for each one, it starts applying Reidemeister moves to those diagrams. And we know that eventually you can find a sequence of Reidemeister moves which takes each one of those diagrams to the trivial diagram. And so the number of moves that you needed is your function f. Okay, so these are equivalent, but obviously what we want is, and this is really the basis of what we're talking about today, is we want to make f as small as possible. How bad, how complicated is that? And so what's known? Well, there's a celebrated theorem of Haas and Lagrange, which gives an exponential. They prove that you need at most 2 to the kn Reidemeister moves, where k is 10 to the 11. Okay, so this is a celebrated theorem of jams, and I'll explain how it works in a bit, because some of the ideas go into the main we'll be talking about. What about lower bounds on the number of moves that you need? Well, there's an obvious linear lower bound. If I have n crossings, I'm certainly going to need at least n over 2 Reidemeister moves, because each Reidemeister move changes the crossing number by perhaps 2. But it turns out there's you can get diagrams which are more complicated than that, which require more than a linear number of moves. There's a theorem due to Haas and Noack that says that there exist unknot diagrams with n crossings which require at least n squared over 25 Reidemeister moves to trivialize. It's a quadratic lower bound. And it was for a long time an unsolved problem to decide where does the truth lie between exponential and polynomial particular, is there a polynomial upper bound? And that's what I'm going to be talking about today, the positives answer to that question. That if you have a diagram of the unknot with n crossings, then there's a sequence of at most 231n to the power 11 Reidemeister moves that transforms it into the trivial one. See? It's a fairly big number, and that's a sign of the complexity of the proof.
If you don't know it's an unknot to begin with.
Well, this will give you, this gives you a procedure for deciding whether it's the unknot. Right? You need to apply all possible sequences of moves of this length.
So this is less than exponential and greater than quadratic. Where's the
What's the
truth
degree?
lie?
That's a good question. I actually really don't know. I think I can get this down to power 10 at an increase of another 10 or so pages of proof. So that's it. I can't do better.
Is there any chance that pass and know it will help you out and find some sequence that doesn't
Well, that's a
third
good,
power or something?
that's a good question. I mean, I don't know how far people have tried to push their techniques, and maybe, maybe one can find other sorts of higher order invariants which would push it up to cubic or something like that. Yeah, it's a good. I don't know. One thing is this addendum, which I really should have stuck in, that in this sequence of moves, you never need to increase the crossing number past, say, 100 n squared crossings. So you have a sequence of moves, and you never need to get, the sequence of diagrams never needs to get more than, say, 100 n squared. That was actually already known. I'll come to that. The fact that you could trivialize it without increasing the crossing number more than quadratically is already known. I'll explain how that's proved due to GTiNY. But that applies to this sequence as well. Okay, so that's mostly what I want to talk about today. But I also want to talk about non-trivial knots as well. Okay, so an extension to this theory applies to non-trivial knots. So you can ask the same question, general question. Given two diagrams of a knot with n and n prime crossings, can one determine an upper bound as a function of n and n prime and the number of moves that you need to get from one to the other? And just as before, the same sort of argument says that the existence of a computable function is equivalent to the existence of an algorithm to decide whether two diagrams represent the same knot. And we actually know the existence of such an algorithm, first given by Harkin and Hemion, although there are now other approaches. And so we know that there is a computable function. But exactly what the computable function is, or qualitatively what it is, it seems a long way off. Let me tell you what's known. So Hasse and Nowick also, their results also apply to not just unknots, but in fact any knot type. So they proved that for each knot type k, there are diagrams dn and dn prime for k, so that these diagrams have a linear number of crossings as a function of n, but the number of Reidemeister moves required to get from one to the other is at least a quadratic function. Okay, so not just for unknots, but for any knot type, we know that the quadratic function has to be quadratic. What about upper bounds? Well, there's a theorem due to myself and Alex Coward, where we give an explicit but fiendishly large upper bound. We proved that two diagrams of a knot with n and n prime crossings differ by a sequence of at most this many Reidemeister moves. So I've left a big space because it's 2 to the 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 n plus n primed. And this is a tower of 2s of height exponentially large, it's c to the n plus n prime, where c is mere 10 prime. So, yeah, it's a big number, but it was the first bound that was known to be primitive recursive. Well, that was just known to be computable. Yeah.
So, in the Haas-Noack theorem, what if you ask about the number of moves you needs to take dn down to k?
dn down to a fixed.
Yeah, to like a fixed, like let's say the minimal representative. Is
Yeah,
that,
right.
Because
Well,
you're taking like a fixed knot type, like the trefoil, and then you're taking these sequences of pairs of increasingly large diagrams, and you're saying it takes a long time to go from this one to this one.
yeah.
But what if you want to go back to say just the trefoil?
It's a good question. What happens if I had just fixed the knot type, fixed like instead of dn prime, say d prime? Just,
Yeah.
not independent of n.
But if that wasn't quadratic, then just by trying.
Yes, of course. Then you could go from one to the other. Yeah. Thanks. Yeah. Yeah. Okay. So, what do I have to say? Well, actually, in general, I can't improve this. I don't know how to do better than this. But I do have the following theorem, which is that if we fix...
Doesn't that mean that that n plus n prime is sort of an illusion? Because I could fix a smallest.
Yeah, but then how? But so, yeah.
There's some constant which depends only on k. And then.
Yeah. I didn't want to make it dependent on k.
Fair enough. Okay, that's a good one.
Here I do want to make things dependent on k. Okay, so in fact, this theorem here, the point of this is that it depends on k. Okay, so you fix your knot type. At the beginning of the talk, we were talking about unknots. Now we're going to fix the knot types, trefoil or figure 8. And the theorem is that then there's a polynomial, pk, with the property that if you have two diagrams for the knot k with n and n prime crossings, then they differ by a sequence of at most pkn plus pkn prime by the most sequence. So it says that if you fix your knot type, then somehow the sort of the space of all Reidemeister moves for that knot type is not quite as bad as we thought it might. This has an algorithmic consequence that for each knot type k, the algorithmic problem of deciding whether a diagram represents that knot type is in the complexity class NP. NP, meaning that there's a polynomial time certificate which certifies that the answer is yes, if the answer is yes. And that certificate is just the sequence of Reidemeister moves which takes the arbitrary unknown diagram to some fixed diagram. Okay. Yeah.
Any way of knowing whether this is NP complete?
That's a good question. In the case of the unknot, it's almost certainly not. The reason is that it's an NP. My theorem gives that, but that was already known before. But it's also in co-NP. Co-NP meaning that if it's non-trivially knotted, then there's a polynomial time certificate which certifies that it's non-trivially knotted. So this result is due to Ian Hegel, and also another version of the result, assuming the generalized Riemann hypothesis, was written down in detail by Greg Cooper. Okay, so that means it's in co-NP and in NP, and it's a conjecture in complexity theory that no problem in co-NP and NP is NP. So that's the case for the unknot. For other knot types, it's not known to be in co-NP. Right? So, and I actually really have no idea what to expect in that case. I really don't. It's certainly it could be the case that say that figure 8 knot recognition is NP complete, but I somehow guess that it's not. Okay, so This is also what I want to talk about today. I'm not sure how much of this I'll be able to explain. But the non-trivial knot case builds on all of the work in the unknot case. So we have to understand the unknot case first.
So, do you know something about how pk depends on k? I mean, is it
Yeah. I was going to, quite bad. So you can also say the degree. The degree seems to be of order c to the l, where c is some fixed constant, say about 100, and l is the length of a certain sort of hierarchy. Okay, so in the case of the figure 8 knot, I've been trying to compute what this number is, and it looks like it's about 100,000. Okay, so yeah, the degree of this polynomial, at least if you trace through my argument, it probably blows up pretty quick, but of course we don't know that it does. Yeah, which gives away that actually it's hierarchies that we can use. Okay, so let's go back to the case of the unknot, and I'm going to do a very briefish survey of what's known about the unknot, and there are lots of bits that I'm going to miss out. In particular, I'm not going to discuss braids at all, and I'm not going to discuss things like covenant homology. In fact, I'm going to start on just the first solution to the unknot recognition problem, which is Harkin's algorithm. So he used normal surface theory. Normal surfaces, as I'm sure you all know, are these guys here. You fix triangulation of a 3-manifold, and a properly embedded surface is normal if it intersects each tetrahedron in the direction of triangles and squares. And so he associated to each normal surface a list of integers, non-negative integers, which just simply count the number of triangles and squares of each type. Okay, so if you've got, say, T tetrahedra, you have a list of 7 T numbers, because there are 7 types of triangles and squares in each tetrahedron. Okay, so this is called the normal surface vector, and I denote it like that, S with little square brackets around it. And these vectors satisfy some constraints. There's the matching equations, which just simply say that as you have a face of your triangulation with tetrahedra on either side, then the normal surface on one side has to catch up with the normal surface on the other to make it embedded. So there's a list of equations that you get. And there's also the compatibility conditions, which, or the quadrilateral constraints, or whatever, there's different names, which just simply say that you can't have 2 different types of square coexisting inside the same tetrahedron, because that would inevitably make the surface non-embedded. So it's Harkin who realized that there's really a 1-1 correspondence between properly embedded normal surfaces up to a suitable notion of isotopy and non-negative integer solutions to the matching equations that satisfy the compatibility conditions. So in some sense, looking at normal surfaces boils down to looking at linear algebra. And in particular, you can talk about the sum of 2 normal surfaces. So we say normal surface S is the sum of 2 other normal surfaces if it's the normal surface vector satisfied. And we can say that a surface is fundamental if it's not a non-trivial sum. So how does Harkin's solution to the unknot detection algorithm work? Well, if you've got the unknot, the exterior of it is the solid torus, and that's characterized by having a compression disk, boundary having a compression disk, or just the meridian disk of that solid torus. Harkin, in fact, I think this actually was known before Harkin that you can, if you have a meridian disk, you can find one in normal form. And that's just pushing and pulling. But this is due to Harkin that you can find one that's fundamental. And also, there's an algorithm to find all fundamental solutions. So that really is just linear algebra. And so Hopkins' algorithm runs by, first of all, you take your knot, you drill it out, forming a knot exterior, you construct a triangulation for it, you find all fundamental normal surfaces, you do that by the second of those results, and you check for each one whether it's a spanning disk. If it is, you've got the unknot, and if it's not, then you know it. Okay, so that's Hopkins' algorithm. And Hopkins' algorithm was the central, was really the central input into the exponential upper bound of Reidemeister moves due to Hasse and Gehring's. So how does their algorithm work? Well, so we now have the unknot, and what we want to do is we want to trivialize it using a sequence of Reidemeister moves. And so what you do is you slide the unknot across the spanning disk. So the unknot it's got some complicated diagram. It bounds a spanning disk which may be complicated, and you want to slide it across that. So as you look at what happens as you slide the knot across the disk, you get a sequence of diagrams. If you're careful, you get a sequence of diagrams that differ by Reidemeister moves. And so what you need to do is you need to control the complexity of that disk. And that's one of the things they did. Again, fairly elementary linear algebra gives you that each fundamental normal surface has, if you're a triangulated manifold with T tetrahedra, has at most exponentially many triangles and squares. Okay, so we know now, so the way that argument works is you construct a triangulation of the knot exterior from the diagram, and you'd be a little bit careful now to make sure that the tetrahedra are nice and straight in R3. You know that there's a fundamental spanning disk, and we've got a bound for the number of normal triangles and squares, and you slide the unknot over this disk, and each, roughly speaking, each slide across a triangle or square leads to a bounded number of Reidemeister moves. And so the exponential upper bound on the number of triangles and squares gives you an exponential upper bound on the number of Reidemeister moves. That's the way that argument works. Okay, so you might ask yourself, can we improve this? Can we somehow get down to a polynomial number of triangles and squares, and hence a polynomial upper bound in the number of Reidemeister moves? And the answer is definitely no. There is no way to improve the estimate on the number of triangles and squares. Okay, so this is a result due to Hasse, Snow, and Thurston, who found a collection of unknots consisting of, each one consisting of straight arcs, this many straight arcs, linearly many straight arcs, which has the property that any piecewise linear spanning disk for that unknot has to be exponentially complicated. It has to have at least 2 to the n-1 triangular faces. So the way that works, it's a very clever argument. The way it works is you start off with just a sort of standard unknot, which is kind of almost like a braid, at least this left-hand bit is like a braid. And then in here, what you do is you insert repeated copies of the same pseudoknot of braid, and then their inverses. Okay? So that hasn't actually changed the knot type. But what it's done, though, is that it has muddled things up inside this region. Now, the disk sliced through between these strings before. And as you apply an nth power pseudoknot of braid, each power that you impose will make the disk inside here more complicated by a definite factor. So by the time you reach this middle portion, it's exponentially complicated. Okay, so that means that you can't just somehow get a polynomial upper bound to the complexity of the spanning disk. Can't be done. So that suggests that you need to come up with a completely different way of solving this problem. And that's what I'm going to talk about now, using rectangular diagrams. So this is there's a major step forward due to GTiNY2013, a bit over 10 years ago, which he gave another unknot detection algorithm. It's based on earlier work of Berman and Manasco, and of Bennekin, and of Cromwell. And it used rectangular diagrams. So here's a rectangular diagram, or a grid diagram. I'm sure many of you know what these things are. They're kind of bizarre. Well, the first time you come across them, you think, what is the point of that? They're just diagrams consisting of vertical and horizontal arcs. No two of these arcs are allowed to be collinear, and they have the constraint that whenever you have at each crossing, it's the vertical arc that's the overarch. The number of horizontal arcs is equal to the number of vertical arcs, and this is called the arc index of the diagram. Okay, so Cromwell analysed arc presentations of knots, and he came up with a sequence of a collection of moves that you can make to a rectangular diagram, which don't change the knot. They're like Reidemeister moves in the sense that any two diagrams of a knot, any two rectangular diagrams of a knot, differ by a sequence of these moves. So here they are. Cyclic permutation of the edges is one of them. So what you do is you look at, say, the leftmost vertical arc, and you pick it up and you move it to the rightmost one. Change the knot type.
So here horizontal things go over the vertical things, is that?
Vertical things go over the horizontal things.
So you're taking that behind.
It goes under, yeah.
Okay.
There's also another version of this where you deal with moving, say, the topmost horizontal arc and making it the bottommost one. And you're going over. Okay, so there's a cyclic permutation of the edges. There are stabilizations and destabilizations, which are described here. Stabilizations make the diagram more complicated in the sense that they increase the arc index. Destabilizations decrease the arc index. And then there are exchange moves. So an exchange move is you're allowed to perform an exchange move if you have two horizontal arcs which are adjacent in the sense that they have no other horizontal arcs with height value between them. So given two adjacent horizontal arcs, there are three possibilities. One is that they're nested like this, where one is longer on both sides than the other. Another possibility is that they're disjoint like that. And then there's a third possibility, which is where they're interleaved like that. So we assume they're not interleaved. And if they're not interleaved, then you can just change their heights. And that doesn't change the knot type. That's the exchange. And so GTiNY2013 proved that any rectangular diagram, it's a very striking result, any rectangular diagram of the unknot can be reduced to the trivial diagram using cyclic permutations, exchange moves, and destabilizations. And as Joan said, this was already known. A version of this was also already known in the case of braids, due to Berman and Manasco. Crucially, no stabilizations are required. So you never need to increase the arc index. So this has the following consequence. Remember I said that you never need to make, there's always a sequence of diagrams where the number of crossings is at most quadratic throughout. This was observed by GTiNY2013. This bound here, and the reason is as follows. You start off with an unknot diagram. You fiddle with it a bit to make it rectangular, so that you can do that without increasing the arc index too much. then you apply this theorem and you never need to move out of the world of arc, you never need to increase the arc index. And if I have arc index at most m, say, then the number of crossings is at most m squared. So I never need to go out more than quadratically many crossings. So this obviously, these theorems obviously give you an unknot detection algorithm, but what they don't do is they don't tell you how many moves you need. They do not give you a polynomial upper bound on the number of moves.
They give you a better exponential.
They give you a slightly worse exponential.
Slightly worse?
Well, the reason is that the number of diagrams with index n is like n factorial, which is slightly worse. Okay. So I need to explain how Dinokov's proof works, and it involves arc presentations. So in an arc presentation, you fix a round reference circle called binding circle, and the complement of that binding circle is an open solid torus, which you view as foliated by disks. Those disks are called pages. So you've got an open book decomposition of the three-sphere. And you say that a link L is in an arc presentation if it satisfies the following two constraints. First, it should intersect the binding circle at finitely many points. These are called vertices. And secondly, for each page of your open book decomposition, that it should intersect that page either in the empty set or in a single arc joining distinct vertices. Okay, so this, for example, this runs in one page from here to here, and then another page from there to there, and then another page from there to there. Okay. So that's arc presentation. And it turns out that there's a 1-1 correspondence between arc presentations and rectangular diagrams up to cyclic permutation. Just very briefly explain why that is. So, for example, to go from an arc presentation to a rectangular diagram, how does that work? Well, to specify an arc presentation, you have to specify the vertices. So those are numbers between, say, 0 and 2 pi, just by an angle around the circle. And you also have to specify the heights of these arcs. Each one lives inside a page, and there's a circle's worth of pages, again, so you can specify between 0 and 2 pi. So for each arc, you have it at a certain height, joining, say, a height t, joining vertex S1 to S2. And so what you then do is you then insert into your rectangular diagram a horizontal arc at height t, going from x coordinate S1 to x coordinate S2. And you do a similar thing to vertical arcs by what happens near each cross, each vertex. Okay, so there's a simple dictionary between rectangular diagrams up to cyclic permutation and arc presentations. And it's really arc presentations that you deal with. Okay, so Dinokov's argument, and so this goes back to Denikin, I think, it's heavily used by Byrne and Masco, uses the singular foliation that a spanning disk inherits. Okay, so suppose I've got the unknot. Let's just go back a second. Suppose I've got the unknot. It bounds a disk. That disk inherits a singular foliation from its intersection with the pages. You can think of the pages as forming a sort of height function on the complement of the binding circle. And that height function gives you a height function on the disk, and the level sets of that height function give you leaves of a singular foliation. There, as I say, there are various singularities. So, for example, there are the usual sorts of Morse-type singularities that you get. For example, suppose I have a local maximum of my spanning disk. Then what I'll see in the sort of contours is I'll see a little dot at that local maximum, and then I'll have little circles around it as you kind of go down the hillside. Yeah?
Do we assume the disk is in general position, so it doesn't lie in no portion that lies within a single phase?
Yes. Yes, you have to put it in general position. And you actually have to be a little careful about what happens near the boundary. It's a bit, yeah. So you have a singular foliation, and some of the singularities are these sort of Morse-type singularities. That's a local maximum minimum. That's a saddle. And then you have these this type of singularity, which is called a vertex. And what happens here is this is as the disk slices through the binding circle. So the binding circle has these pages coming out of it, and as the disk slices through the binding circle, you see this sort of star-shaped singularity.
So is Dinocoff assuming that his unknot bounds a disk to get the information?
Yes.
But isn't that what he wants to know?
Well, what you do is you assume you bound the disk,
Yes?
show that implies that there's a move that you can do. And then,
That you show the existence of Reidemeister moves.
yes.
But then you know it's the unknot, and then you're just asking to count the number of Reidemeister moves.
Well, of course, Dinocoff wasn't so concerned with Reidemeister moves. He was concerned with these exchanging moves. He wants to show that you never need to stabilize. Yeah. But what I need to do is I need to count moves. Okay, so you have this type of singularity as you slice through the binding circle, and then you have these type of singularities near the boundary of the disk, which we won't worry so much about. You can't see this bottom line. I couldn't get this thing down any further, but what it says is that a separatrix is a component of a leaf which, so there's certain special leaves of this singular foliation which end on saddles. Those are called separatrices. And the valency of a vertex is the number of separatrices coming out of it. And so the point is you get this sort of this graph inside your spanning disk, where the vertices of the graph correspond to these vertices here and the saddles, and coming out of these saddles you have these special singular fibres. And where do they end up? Well, you might think that you might join a saddle to another saddle, but you can arrange that never happens, because you can arrange that the saddles all have different heights. And so that means these leaves are level sets lie inside a single page. So you never join a saddle back to another saddle. You might join a saddle to itself. That's a kind of special case, which I don't worry too much about. The generic situation is where one of these separatrices ends on a vertex. So you just end up with this sort of graph. And you analyze the graph, and you apply the fact that the disk has positive Euler characteristic to deduce that there exists a vertex with a certain form. So there's either a pole, a local maximum minimum, and that's a simple thing to deal with, or there's a 2-valent interior vertex, a 3-valent interior vertex, or a 1-valent boundary vertex. And in each of these cases, there's something that you do which simplifies the disk.
Right, so, but the boundary of the disk is not included in the separatrices? So what's the valency of your examples?
Well, you can't see, because you can't see the separatrices. This is The boundary of the disk is, yeah, it's not a separatrix.
Right, but so in E, that's valence 1?
That's not a vertex.
Well, that's not a vertex, yes.
That's a vertex.
So you don't see any of this information unless you already know you have the unknot, and then you have the surface that it bounds, right?
Yeah.
The disk.
Exactly.
All right. So he's going to give you a bound on the number of Reidemeister moves, but then you're going to have to try many, many more Reidemeister moves if you want to use that for an algorithm.
Yeah,
right?
it's
Yeah.
a classic NP algorithm.
Yeah.
It relies on unknown information. Yeah, that's exactly what I want. But we don't know better than NP. I mean, there's no algorithm which doesn't.
But this is exactly the same thing that Manasco and I did with braid foliations. It's just a variation on the same idea.
It is a variation, except the fact is that in the braid case, you don't have finite many exchange moves. Right? Whereas in this case, there are only finitely many exchange moves that you can do. So what you do is you keep track of the main measure of complexity. Well, the main measure of complexity is the arc index of the arc presentation of the knot. But it turns out, well, we'll see. Yeah, that's what. At least that's the way that GTiNY sets it up. The second measure of complexity is, and really, in fact, the one that most of one focuses on is the complexity of the disk. We're simplifying the disk. And the way you measure the complexity of the disk is you count its number of singularities. So in each case, you want to reduce, you say, aha, I see one of these, and so I need to reduce the complexity.
Mark, I'm really sorry. Could you just draw pictures of what a two-valent material
I'll
is?
show you.
Okay.
Yeah. Okay, so in each case, if you have one of these type of vertex, there's something that you can do which will reduce the complexity of the disk. I'm going to seriously run out of time if I'm not careful. And that requires, as the cost of performing some exchange moves, cyclic permutation, and maybe a destabilization, but you never need to stabilize. Okay, so this is an example of a one-valent boundary vertex. There are two possibilities for a one-valent boundary vertex. There it is, and there it is. And let's focus on this type here. And you see inside the arc presentation a sort of arrangement like this. Okay, so this bit of link there is that bit of link there. That there is that there. That saddle X is that saddle X there. And what you do is you slide the knot through here and through here, keeping it level until the height of this arc is adjacent to the height of this arc. And then there's an obvious move that you can do which just pushes that and makes the link like so. And then that reduces the arc index by that. You've destabilized it. This move of moving this link up this way and that bit of link that way, that might actually force you to perform exchange moves. Because there might be other bits of the link with heights, which are sort of at this height here, on these heights there. So you perform exchange moves, there's a cost associated with that. Here's a two-valent interior vertex. You can see there are two separatrices coming out of it, one going down there, one like that. And you get an arrangement of the disk, which looks a bit like this. Hard to draw. And it goes. And then you should. There's a move that you can do, which essentially switches this bit of surface, reducing the number of singularities, the number of vertices by 2. Yeah.
So in the two-valent interior vertex, what does that look like? What more singularity is that? I mean,
this is just a normal saddle there. There's no boundary anywhere nearby.
I see. And the thing is, I see. So this is a case where you have two saddles on the same level, or?
No, this is a different level from this. It's coming out.
Oh, I see. They're going to the boundary. I see, okay.
Yeah, this is a bit of the boundary there. It takes
It's
some time to
interior,
see
it's
why.
interior on the disc, but it's a place where it's intersecting the binding.
Yes.
Okay.
Yes, exactly. So the knot is a million miles away from here, but it is still intersecting the binding circle. Yeah.
Why aren't the horizontal line segments separation sheets?
Yeah, they look like it. Yeah, but they're not. A separatrix is by definition one that runs from a saddle to a vertex. This runs from vertex to vertex. In fact, generic fibers run from vertex to vertex. So there's actually there are only two special fibers there.
So I guess I didn't understand your notation. Does that say S1, S2, X1, and X2, or
Yeah.
the 4 points there?
Yeah. So this is S1, S2, X1, X2. So not very clear. Okay, so there's a push that you can do. Now, the problem is that there may be stuff in the way. But there may be bits of knot and bits of disc lurking here. Well, there may be bits of knot and bits of disc lurking inside here, which escape through this little gap there. So you need to get those out of the way. So it turns out that what you should do is you should pick up the stuff that's here and the stuff that's here and then swap them over. And movements and exchange. It turns out this is expressed as a sequence of exchange moves. Okay, so it does matter how the details of this work. I don't have time to maybe explain it in much more detail. This is all been worked out by others, not me. But so the key is you've got to get stuff out of the way. That has a cost in terms of exchange moves, and then you can isolate the surface and reduce its complexity by 2. Okay, in the case of a 3-valent interior vertex, I'm not going to describe. So how does my proof work? Well, what you do is you combine normal surface theory with Dinokov's. Okay, so you combine the two theories. Now, they don't fit together particularly well, but you do your best. So first of all, the normal surface theory to apply, you need a triangulation. There's a triangulation that was described by Dinokoff, which is a very natural one. So if you have arc index n, then you can create a triangulation of the 3-sphere by realizing the binding circle as a polygon with n corners, the dual circle as a polygon with n corners, and sort of taking the join of those two triangulations of the circle. So a typical tetrahedron looks like this thing in light blue. It has n squared tetrahedron. So this is a triangulation of the 3-sphere in which a link turns out to be simplicial, and in which the binding circle is simplicial.
Is this in Dinokov's paper or is this yours?
This is Dinokov's. Nothing I've said has been my work. Apart from
The theorems.
that. Right, so, slightly unfortunate 5-2. Anyway, right, what do you do? Well, the outline of the proof is as follows. You start off with a diagram of the unknot with n crossings. And then you fiddle with it a bit until it's rectangular. Okay, so just make the edges horizontal or vertical. And that has a slight cost, but make it up to arc index, say 7n. You could do better than that, actually. So we've got arc index 7n, so from this we get a triangulation of the 3-sphere with 7n all squared tetrahedron, in which the knot and binding circle are simplicial. So then we know that we can find a spanning disk with an exponential upper bound on the number of triangles and squares, and hence an exponential number bound on the number of times it intersects the one skeleton of the triangulation, and in particular an exponential upper bound on the number of times it intersects the binding circle, which is our main measure of complexity. Okay. So we've got a spanning disk with at most this many vertices. Now we know that there is a 3-valent or 2-valent interior vertex, or a 1-valent boundary vertex. You can make sure there are no borders. And here comes a key bit of red. So if you had such we know that for each one, that would specify a a move which would decrease the complexity of the knot. But let's suppose that we can find a large collection of these with parallel stars. I'll explain what that is in terms of this picture here. So this bit of surface is the star of this vertex S here. It's all of the leaves that are incident to S. So we can say that two such stars are parallel, well, if they're parallel as normal surfaces. So what that means is you say you had two of these, and you have another bit of surface which did almost exactly the same thing. So I had lots of these. Then what can I do? Well, what I can do is I just do the move that I did before. I want to just push them all through at the same time. And then for each star, I reduce the binding weight by 2. So if I have loads of stars, loads of bits of the surface, I'll reduce the binding weight by a lot. Now I might have stuff in the way, as I had before, but I only need to get it out of the way once. I get that stuff out of the way once, and then I can reduce the binding weight by a lot. So the idea is that you want to try and find lots and lots of these vertices with parallel stars. And then what you do is, instead of decreasing the binding weight by a factor of, by just 2, you decrease it by a definite factor. If I decreased it, say, by like 1%, then because I had exponential binding weight to begin with, then after just, say, if it was 2 to the n squared binding weight to begin with, if it was just by 1% each time, I would be able to get it down to just no binding weight at all, by 1 in n squared steps. Okay? Now you don't do it by a definite factor, it's not by 1%. It's by this much. Well, even this is a lie actually, but let's say it was this much. Then you would then, after polynomially many steps, have reduced it down to nothing. Okay, so that's what we're trying to do. So as I say, parallelism is really defined in terms of the triangulation. So we use normal surface theory for two parts. Well, actually quite a few different parts, but the two main parts. One is to get an exponential upper bound on the initial complexity of the disk. And 2 is to talk about parallelism. Talk about two bits of surfaces being parallel. So two bits of normal surfaces are parallel in the obvious way. Two triangles of the same type are parallel. So you can use this to talk about two stars or two vertices being parallel. So just as in a triangulation, if I had, say, n tetrahedra, there are at most 5n types of triangles and squares that simultaneously exist inside that. Well, the same principle applies to the star of vertices. There's a linear number of vertex types. So the number of stars of the number of types of stars of vertices come in at most this many types. 5, remember this is again a line, but it doesn't matter. Morally correct. 5 is the 5 we had previously, and this is capital N, the number of tetrahedra. So we know that there is some 3-valent or 2-valent interior vertex. Suppose we had V vertices, and suppose, and this is a big supposition, suppose the number of vertex number of vertices of each type was uniformly distributed amongst all the different vertex types. Well, we know that there are at most this many types of vertex. So therefore we would know that if there were V vertices, there would be this many types of, this many vertices of 3-valent, 2-valent, or 1-valent, all of which were parallel. Okay, so that means that we could then reduce the binding weight by this amount, which would reduce the binding weight by the factor that I had before, 1 minus 1 over n squared. Okay, so if we knew that there were lots, if we knew there were lots and lots of 2-valent, 3-valent interior vertices rather than just one of them, we'd be done. But we don't know that. So the analogy is with planar graphs. Okay, so it's well known in the case of planar graphs that you've always got to have a vertex valency at most 5. That's a well-known fact. But it's not true that if I have So the analogy here is that we've always got to have a vertex of valency in those three, interior vertex of valency in those three. The analogy here, but if I have a planar graph with loads of vertices, it's not true that a definite proportion of them have to have valency, like those 5. You may have lots and lots of vertices which have valency 6. Right? The point is that, so the valency 5 ones, in the planar graph case, they kind of contribute positively to Euler characteristic. The ones of 7 contribute negatively and above contribute negatively, and the ones of 6 don't contribute at all. They're Euclidean. Well, the same principle applies here. We may have lots and lots of Euclidean vertices. In our case, Euclidean, here's what is true. Right? So the Euler characteristic argument implies that either you have lots and lots of 3-valent or 2-valent interior vertices, so the above reasoning works, or you have lots and lots of vertices which don't contribute to Euler characteristics. These are 4-valent interior vertices, and they look like that. These guys are bad guys. You can imagine whole loads of these stacked together in some huge grid inside your disk. And how the heck do you deal with those? It turns out that there's no move that you can do to just get rid of them. They sort of inevitably have to exist, and the reason you know that is, for example, if you're looking at, say, satellite knots. They're essential tori, and you can push and pull until the torus consists entirely of these guys. So suppose you have loads and loads of these. Well, it turns out that a rather subtle argument involving branch surfaces gives you that if you had lots and lots of these guys, then they would stack together to form a normal torus summand for your disk. You would be able to show, you could find a big chunk where the itinerary of this top bit going along here followed the itinerary in the 3-manifold at the bottom bit and left or right. And so that would give you a normal torus summand for the disk. And that would then contradict the fact that the disk was assumed to be fundamental. Okay, so the fact that you get this, you can show that you have this normal torus summand, this is, you know you're in dangerous territory because in some sense you're kind of in the realm of sort of aperiodic tilings of the plane. Each of these guys has a like a colour. It's a vertex type, and there are only finitely many colours. But how can we make sure that we get a sort of a repeating pattern so that this top bit follows this bottom bit? And you can imagine scenarios where you kind of avoid that sort of repeating pattern. But it turns out that because this is all being carried by you're sitting inside a 3-manifold, being carried by a branch surface, you can arrange that it doesn't happen. But it's quite a difficult argument, actually, but you end up by showing that contradict the initial assumption that the disk is fundamental. So this is another part where you have to use normal surface theory, quite an essential bit. So that's a rapid summary of the unknot case. The non-trivial knot case, I will just simply say that you do exactly the same. Okay? Except you have everything you need. You have normal surfaces, you have arc presentations. What you don't have is a spanning disk. Right? So instead of a spanning disk, you use a hierarchy, a special type of hierarchy. And you apply the same sort of arguments to that. Okay, I'll leave it there. Thanks.
Are there any questions for Mark?
Yeah.
Yes, recognizing split links, do you have to do the stabilization of 7n for the unknot case? Or
Well, actually, so that 7n wasn't really a stabilization. It was just a way of getting these diagrams straight.
Oh, okay.
It was just a question. There's this.
That's getting any grid position.
Yeah.
Oh, I see. Okay.
Yeah, I didn't stabilize. Well, so in the unknot case, so yeah, the way my argument works, I actually, one of the technical bits, I actually have to use a type of move which does stabilize, does an exchange move, and then destabilizes again. So I slightly differ from Blinikov. The reason I did, but in the split link case, you don't need to do that. It's all to do with the hassle of dealing with what happens with the boundary.
Are there any other questions? Let's thank Mark again.